So now we have 2 raised to k r factorial designs. What is R? R is actually for replications. So now if you do each experiment many times, the numbers would be different. So how do you take care of that, and what does it tell? So we will worry about all of the same thing that we did before with replications, computation of fx, variation, tests, and so on and so forth. So the model changes slightly. We have a new term in the model, and that is the E. With 2 raised to k design without any replication, you had 2 raised to k numbers or measurements and 2 raised to k unknowns are the effects. Right? So the number of unknowns was exactly equal to the number of effects, and therefore there was no error. It was a linear equation, you solve it perfectly. And every number will come out exactly as you measured. The prediction will come out exactly as you measured. Right? There was no error. So E term was not there. But now, I am coming to that. Now, because you measured it many times, and each time the number is different, basically there is something that you are not controlling. There is some noise. And therefore, so now you could have 2 raised to k r experiments. R could be, let's say, 2. You repeat every experiment 2 times, or each experiment 3 times. R could be 2 or 3. Now with that many observations, you have only still 2 raised to k effects. So you have some errors that have some degrees of freedom. In the previous example, in the previous case, the errors had 0 degrees of freedom. Basically, there were no errors. Now you have some errors, and so now we'll worry about that model. Now this is actually, as written, is only 2 raised to 2r experiment. 2 raised to 2r will be 2 factors, but k factors is straightforward. Yeah. Question now. Go ahead.
Obviously, there were no errors because you measured only once.
Yeah. So there was no measured error basically. Errors probably were happening, but you didn't measure them. All right. So now let us see. It's very straightforward, and we will actually move fast forward in these one or two chapters because things are very straightforward. So you measured y, it came out 3 times. All you do is get the mean of that measurement, do the table as before, sum it up, get the factors, you get the effects. Okay? And the main thing is that your estimated response would be, basically y hat would be this value plus E would assume 0. So this would be your y hat. Your error will be equal to the difference between y measured minus y hat. And obviously your goal of the model is to have 0 mean error and minimum mean squared error. So the mean error is 0, and this sum of the squares would be minimum when you do exactly what we showed you in the previous slide. When you do this thing in the previous slide, that will give you the minimum squared errors. And so the errors can be calculated for each of the observations by calculating y hat and then subtracting from the observation. So in this case, if there were 3 values measured, the mean was 15, so that is what you are going to predict. Your model will predict y hat 15, and so the error would be 0 in this case, 3 in this case, and minus 3 here. Similarly here the error is minus 3, 0, and 3 because you are subtracting from y measured to y hat. So these are your errors, and as you can see, the errors add up to 0. Actually each row adds up to 0. Right? So they add up to 0, so that is the case, and this is the minimum error you will get. By any other model you will get more errors. I mean, for any, let me correct, it's not for any other model. With any other values of the parameters, using the same model. See, if you change the model, the whole thing will change. So let me just say this. If you assume a linear model like this, then the values of q's that will minimize the sum of squared error is that. Okay. If you change the model to something different, which we will see in a minute too, different kind of models. But if you keep this kind of model, then your best bet is to use these values of q's that we calculated, and this is the minimum squared errors you will get. Now, so we have these errors and we have sum of squared errors. Now we can divide into 5 parts. SST, the total sum of squares, is equal to SSA, SSB, SSC plus SSE. Okay. So you can calculate this way, and then basically these terms, and then you can see what contributes how much. All right. Then we can do the percentage variation. Now, so let's see. SSY is 27,000. SS0, basically it was y bar squared kind of thing, is 20,000. So the total variation is the difference of these two. SST is SSY minus SS0, which is 7,000. So the total variation in y is 7,032. Now that can be divided into 5 pieces, or 4 pieces actually. SSA gives you 2 raised to 2r qa squared. Remember, there is an r term here. So 5,547. SSB gives you 1,083. SSAB gives you 300. And if you add them up, they will add up to 7,000. And with errors, along with the errors. Errors are the remaining of that. So that is, errors is 102. So if you add up these 4 numbers, you will get 7,000. So you can put percentages on them, and you can say that the A explains 78.88%, B explains 15.4%, AB explains 4.27%, the errors explain 1.45%. So the good news is that the errors are very little. What it means is that the factors that you didn't control had very little effect. So that's good. At least you controlled everything. And the second thing it says is that you really want to worry about A more than anything else, because it is 80% almost, 78.88%. Alright, if you have time, then go for B. And then if you have time, then go for interaction AB. Alright. So one thing new with the R replications is that we can calculate the effect of things that we didn't control. All right. Now, but there are a few more things we can do. First thing is we can do confidence intervals. But before I do confidence intervals, we need to calculate the degrees of freedom. And I think the best place to calculate the degrees of freedom is right here, maybe. Let's see. This one, how many degrees of freedom are here? Maybe here. Let's look at here. You see, we are calculating yi minus y hat. For each row, yi minus y hat, if I gave you 2 of them, then you can figure out the third one. Right? Because this y hat is calculated from these 3 numbers and not from any of these numbers. So this 15 was calculated from these 3. So if I give you 2 of them and this number, then you know the third one. Right? So there are only 2 degrees of freedom. So the errors here have 2 degrees of freedom too. If I gave you any 2, then you can get the third one. So the total degrees of freedom the errors have is 8. Eight degrees of freedom. So, yeah. 2, 2, 2, 2, 2. 4 times 2. Alright. So with that, actually that gives you the formula. 2 raised to 2 times r minus 1 is the degrees of freedom. 2 raised to 2 times r minus 1. This is the number of rows that we had, and r minus 1 is the degrees of freedom, for each row. So if you have that, then you can calculate the standard deviation of errors. Standard deviation of errors is simply the sum of errors squared divided by 1 upon the degrees of freedom. And this is also called MSE, mean squared error. So the variance can be calculated by this formula, or mean squared error can be calculated by this formula. Once you have that, you can calculate the confidence intervals of the effects. Okay, we are assuming here that the errors are normally distributed and with zero mean and this standard deviation, and therefore basically you can calculate the effects. So the effects standard deviation is SE upon square root of 2 raised to 2r, which is actually basically 12 in the previous example. 2 raised to 2 is 4 times 3. 3 is the replication, square root of 12. So each of these effects have same standard deviation, and therefore confidence interval is simply the mean minus plus t value times the standard deviation. If the confidence interval does not include a 0, then it is significant. Okay, not important, significant. And we will see this kind of stuff in the example in a minute. So for the memory cache study, SE would come out 102, which was the sum of squared errors, divided by 2 raised to 2 times r minus 1. R is 3, so that is 8. 8 degree, actually 8 was also degrees of freedom. So that is MSE is 12.75. Square root of that is 3.57, which is the standard deviation of errors. For the effects, it is further divided by square root of 12, so we get 1.03. For 90% confidence interval with 8 degrees of freedom. For 90% confidence interval, we read t value at 9.5 and 8 degrees of freedom, which is 1.86. And the confidence intervals come out like this. None of them are 0. So all of them are significant. Yeah, go ahead.
So do you recommend it when we calculate degrees of freedom by table or count them from the table?
Calculate what?
You can calculate degrees of freedom by using R.
Oh yeah, this is actually, this will be in Excel worksheet, so you really don't have to worry about it. I just put the value R here and you get it. And this is not a calculation. The calculation is simply calculating SSE. That you have to decide how you do SSE. And
you needed a degrees of freedom.
Degree of freedom is 2 raised to 2 r minus 1 times r minus 1.
Yeah, but you also counted them from the table.
Yeah, so exactly the same thing. It will come out the same.
I know, but why did you do the table?
Oh, I just wanted to explain to you.
I see.
The table explains. This one doesn't explain. This is just a formula here, right? So why did I put r 2 raised to 2 r minus 1 here is because there are 2 raised to 2 rows. Each row adds up to 0, and therefore it has r minus 1 degrees of freedom. Let me just say it again. You see, each row has 2 degrees of freedom. So I said 4 times 2 is 8. So you don't have to calculate it from the table. You have to understand from the table that how 8 number came about. All right. So the key thing is that all of these parameters are significant, and a statistician will tell you that you shouldn't ignore any of these. They're all significant. All right. But let's become an engineer. And as an engineer, we would say, what percentage does it really explain? All right. So QA square and QB square and QC square, I don't have the numbers here, but I can tell you that this is like 20 and this is like 10. QA is 4 times more variation explaining than in B, right? And then B is explaining about 9 times more than the interaction. So, the A is really the most important parameter. And depending upon QAB, I don't know what percentage it is, but this could be unimportant. It's very small percentage. right? Even though it is significant, statistically significant, but if I had a choice, I would spend time there. If I have more time, I will spend time here. If I have more time, I will spend time there. Yeah.
So what if one of your factors is very important but statistically insignificant? If the confidence interval crosses.
Right. Now, that is possible. What is going to happen is that what you are saying is that you did not do either enough replications or something, so you cannot be very confident. So you are making a statement like this: oh, this factor A has 80% of the variation, but I don't know about that 80% because it is not significant.
Okay.
Right? So that means you really didn't do enough replications and things like that. So you will find that out. Then only your confidence will be so wide that it will include a 0 for a large value like 80%.
Okay.
Right? So that can happen, but I mean that's rare. Generally the most important parameter will generally be significant, because for that to include a 0 means everything else will include a 0.
Okay.
You see, all of them have the same breadth. 39 to 42, 19 to 23, they have the same breadth. Right? So if this includes a 0, then, and if this is so wide and it is big, then all of them will be 0. And then you will say, well, there is something I have missed here, which is that you have lots of errors. You have lots of errors. Eh?
So you basically just didn't do the experiment.
Yeah, actually, I think what most likely will happen in that kind of experiment, that the errors will explain 80% of the variation, and your model explains 20% variation. And out of that 20%, maybe 15% goes to A, 5% goes to B, so there is small percentage. Errors would be the most percentage.
Okay.
Yeah.
If we look at slide 4 though, Q0 explains the most.
Okay, Q0 is not explaining anything. By the way, Q0 is the mean. Yes, I mean, like if you want to call that explaining, Q0 is the mean. And so if you didn't want to use any of this model and you just wanted to use, like we talked about in regression, what is B0? B0 was the mean. If you didn't want to use any factors, then you can simply take the mean of all 12 observations and say, well, here is my model and here is my prediction. Just the mean. Everything is noise. So Q0 is actually simply the mean. And so that one, yeah. Okay. So that is like, if you had 0 factors, so that is a Q0. Okay. All right. Now the interesting thing is you can do confidence intervals. See, the one part is that everything that is you are doing in the measurement is random. So we talked about the mean is random. Then we talked about the parameters are random. Now you could have some functions of parameters. And oftentimes people want to do some contrast. What is a contrast? Contrast is defined as some linear combination so that the coefficients add up to 0. And you will see in a minute. But before I go to the contrast, if you take any q values, don't have to be all of them, some q values, and you multiply them with some factor h, and you add them up, such that the h adds up to 0. First of all, h adds up to 0, then this thing is called a contrast. So variance of the contrast can be used by this formula, and you can use the same t interval as before. Alright, so let me give you an example of a contrast. So let's say you want to measure the QA plus QB minus 2QAB. Why? I don't know, but for some reason. And we'll see some valid one. This one is actually totally just an example here. So the coefficients are 1, 1 and minus 2, they add up to 0. So this is a contrast. So the mean of this contrast, U, is QA plus QB minus 2 times the mean of QAB. And that will come out to 21 because you know QA, you know QB, and you know QAB. Variance will be used by that formula that we just had a minute ago, which was SE square times sum of HI squares. Sum of HI squares. SE square times sum of HI square divided by 2 raised to 2R. So in this case, SE square times sum of HI square, 1 square plus 1 square plus 4 square, sorry, plus 2 square is 6. So that is 6. Is this number 6 comes from 1 square plus 1 square plus 2 square. So you put HI squares here, sum of HI squares, and then divide by the total observations, 2 raised to 2 times R, 12. This is the variance. Standard deviation is just the square root of that. And then you take the t value as before and get the confidence interval, so it's still significant. All right, that's about the contrast. Any question about the contrast? Yeah.
Did you just choose the values 1, 1, negative 2 arbitrarily?
Yeah, this is just an example. Actually, a more common thing would be simply QA minus QB. QA minus QB is a contrast. It sets up to 0. Right? And why would you be interested in QA minus QB? Because you want to see the difference between the effects of A and B. So QA minus QB would be more representative example of what you would use. But here I just added up QAB just to show you an example. You can apply here too. Alright, now you could do the same thing for predictions. When you predict, you will be predicting the mean. I mean, y hat is actually exactly this because error is 0. But this y hat is a random number. Its standard deviation depends upon how many observations will you take. So mean of m responses will have this formula, where the n effective is the effective degrees of freedom, which is the total number of runs divided by 1 plus sum of degrees of freedom used in y hat. In y hat, this one had 1 degree of, so basically 1 plus sum of degrees of freedom used in y hat, n effective. Okay, total number of runs is 2 raised to 2 times R, and the number of degrees of freedom in the parameters. So we used 1, 2, 3, 4 parameters. Each of them have 1 degree freedom, and therefore you have 5 here. Confidence interval same way, just with p values. And the m is the number of observations that you will take in the future. If you just take one observation, you put m equal to 1. If you take infinite observations, you put m equal to infinity, and that term will go away. So the example is memory cache study, and you want to predict what will happen with xa minus 1. You have already measured. This is here the thing, and this is more of an example here because you have already measured 3 times the value. Now you're going to predict. Your prediction is going to be exactly the same mean. The main thing is that if you want to be sure that in the future that mean shows up, then you have to say how many observations you will take. If in the future you are just going to take one observation, then your variation will be large, and that would be 4.25. Your confidence interval would be this. Alright, you have already measured 15 out of 3, but basically now your confidence interval says that the next measurement that you take, the 4th one, could be anywhere from 7 to 22. On the other hand, well, if you are going to take 5 experiments, just for the sake of it, 5 more, so you have already have 3, and based upon that you are predicting 15. Well, that would be, if you are going to take 5 more, then your confidence interval would be this, 9 to 20. So the mean of 5 will lie in that interval, 90% time. If you are just going to take large number of observations, not 5 more, then your confidence will be this much, and so on and so forth. You can keep going.
So what is a large number of observations?
Okay, so basically 3 observations is a small number. Now large number means, suppose, whatever number, I mean basically theoretically it is infinity, but somewhere close to infinity. If you take, now here I think, having said that, you really don't need infinity because 1 upon m has little effect, not too much. So here I think, let me just say this. If you put m equal to 100, alright, 5 by 12 is like half, and 1 upon 100 is 0.01. It will be close to infinity. Okay, so basically what I am doing here is going over everything that we did in regression, redoing here with 2 raised to 2 experiments, and now with 2 raised to k experiments in a minute. All right, so let's see, where are we? So we did the confidence interval. There is one more thing here which I want to bring out here is, suppose you don't want to do the future measurements, you just want to say that the mean is 15. Then this formula will become basically, this is the confidence, this is your standard deviation, and this is your confidence interval. And the formula can also be thought of as a contrast formula where you use this model, the model which is the original model like this. This is a contrast because they add up to 0. If you add up 1 plus xa plus xb plus xab, they add up to 0 for all values. You see here in this row, every row adds up to 0. 1 minus 1 minus 1 to 1, 0. This is 0, 0, 0. The coefficients, the coefficients of, maybe this is not the right place. The coefficients of A, where are you going to say? Oh, I lost it, right here. Current mean response for each row is going to basically have this formula which is going to add up to xa plus xb plus xab. The QAs will add up to 0, not the XAs. QAs will add up to 0. So basically this is, so for that the HIs will become equal to 4. Some of these HIs will become add up to 4. HI squares, 1 square plus 1 square plus 1 square plus 1 square 4 times. And then you get this standard deviation using the contrast formula, and you get the confidence interval for the current mean for that row. All right, so now we have a homework. Let's see. This is just a repeat of 2 raised to 3 design, 2 raised to 2 times 3 design. So we have 3 values of A, 3 values of basically 2 factors, A and B. And you have to prepare the table and do the effect. Now let's see, it says each determine the effect. So this is kind of simple. We should have more than this. So this one is simply saying that you determine the effect. So all you have to do is find out Q naught through QAB. Right? So maybe we'll wait for the next homework where we have to do all of this stuff that we did, which is the confidence intervals and other things. All right. Before, so the next thing we did in regression, and we are going to repeat here again, is to verify the assumption visually. So what are the assumptions we made in this design? First, we made that the errors are statistically independent. This is always common assumption. All right? That the errors are additive, and this is very important assumption because we just put the plus E. Errors are normally distributed because we are doing t distribution for that reason, right? Errors have a constant and standard deviation, so they are not varying. And the effects of the factors are additive, that A and B add XA plus XB, right? And if you make all these 5 assumptions, then your conclusion is that the observations are independent and normally distributed with a constant variance. And all of these formulas that we did the confidence and statistics and this and that, all are based upon these 5. So we have to verify these 5. So how do we verify these 5s? So let me ask you, without going too further, maybe it is in the next slide next, but basically let's do, how would you verify that the errors are statistically independent or they are not dependent? Yeah, go ahead.
Plot them and see that there is no trend.
Yeah, you are going to say the same thing?
I was going to say we could also run dependence tests, even though we can't tell if it's independent, we could rule it out by using
Yeah, so visual, since we are visual, we will do visually. Now the errors are additive, kind of difficult to verify right now. Errors are normally distributed, we know how to do normal distribution. That's the simplest one. What is that? How do you verify normal distribution? Yeah, QQ plot. Errors have a constant standard deviation. Again, we will just see whether they are, they look like constant. And the effects of factors are additive. That is difficult to verify. So anyway, so how do we verify independent errors? Scatter plots of residuals versus the predicted response, and then we look at the magnitude. If the magnitude is small, we are happy. If they are large, then we worry about the trends. We can also plot the residuals as a function of the experiment number. We can see the trends. Normally distributed, quantile. Constant standard deviation, we again look at the, how the spread is. So this is what we do for this study. So for the memory cache study, these are the 12 errors, and this is the predicted response, and this is the residual. So the key thing is to look at the y-axis. It goes up from -5 to +5, but the x-axis goes up to 80. All right. So if you don't care for 10%, then this is a small error. Okay. QQ plot shows good enough, so that's good. However, so this is all about this model. However, believe it or not, while doing these things, while teaching these things, we discovered some problems with these models. And so some of the students who did the project just like you, and they came up with some conclusions which were not valid. So they said, sir, this doesn't look like the right thing. What is wrong here? And we discovered what we call multiplicative models. Now, it's not that we discovered in the sense that people didn't know before. Yes, people knew about the multiplicative models before, but this is all in the agricultural field and the medical field. In computer science, we didn't. And so this is an important thing to notice now. So the thing is, what is a multiplicative model? Here we assume that everything adds up. This is not a valid model if the effects do not add up. For example, execution time of the workload. Remember in the exam you had this workload thing with things multiplied? Well, there are lots of such things in the computer science which multiply. So the processor speed times the workload size, they multiply. Alright? But if you take a log, then they add. So for example, execution time is, now let me be sure that this is correct formula. Execution time is Yij is equal to Vi. Vi is the instructions per second. No, this is not the correct formula, right? There has to be a division here. This has to be Wj upon Vi. Right? So this is seconds is equal to instructions divided by instructions per second. So this would be, not a big deal, but basically this would be Wj divided by Vi. It's still multiplicative if you really want to call it, it's multiplying. So you take a log of it and it becomes additive. Right? And so that would be the model. So for this kind of thing, you know that they don't add up. If you are measuring execution time and you have a processor and you have workload, you know that the workload and the process don't add up. Okay? So before you do that, you have to take a log, and now they will add up.
So, okay, processor and workload, they don't add up. But I also don't know that they will multiply.
Yeah, right. The thing is, this is where the system knowledge comes in. So what will happen is if you do this thing, and we will do this in both ways, additive, you will come out with some really crazy conclusions, and you'll say, sir, this doesn't look like right, okay? That's when you start looking at, is the model really good, right? And then the system people will say, well, I think this is, you know, this thing has this effect, and then you will say, oh yeah, if you come up with something like multiplication, then you have a multiplicative model, and then all the inconsistencies will be gone. So so the thing is, it could be another transformation. So just like we talked about other transformations in regression, those transformations will come up too in a minute. But first, let's do the multiplicative model. So once you get the multiplicative model, then you take the antilog and you get the effects of, and basically and then you start talking about the geometric mean, because your Q naught is the effect before the antilog. After the antilog, things just, whatever I was adding is multiplying. Alright, so let's take an example of this. So we measured the execution time of 4 workloads. So these are the work, so let's see, of 2 workloads in 2 processors, okay? 2 workloads and 2 processors. And so the execution time was that, these are the combinations. And if you do the mean as the usual from before, you will come up with something. But before we do something here, one thing you have to do, and this is another art form now you will learn, and I probably have already learned before because we have talked about this before. You look at the numbers you are adding to get these means. So you got the mean of 2655. It is a mean of these 12 numbers, right? What are these numbers? They are going from 0.01 to 85. All right, you are adding numbers which are very different. The range is 10⁴. Right? When you find yourself doing such things, then you know that you are doing it wrong. You cannot be taking mean of things which are so wide. And that is the first thing. Y max upon Y min is 12,534, and therefore when you have such a thing, then you have to see what can I do to reduce this range. And that is one way you will find out that maybe I should try multiplication, because maybe I should try log here. Okay. So basically this is the giveaway, that you don't want to add up numbers which are so different. And if you did use that model, this is what your test will fail, because now you do the predicted response versus residual. The scale here is 160, the scale here is 50 to minus 50, 100. Right? So the errors don't go down. All right. So, and the error is 0 here, and then this is like that. It doesn't look like constant error standard deviation either. So it fails that test as well. And when you do the QQ plot, doesn't look like a straight line to us. It looks like totally different straight line. And so on. So you will find lots of inconsistencies. And one of them will nudge you towards the multiplication. So basically we take the log, and once we take the log, we do the analysis, and then we plot. Okay. So now when we plot, the range here is 2 to minus 2 predicted response, and here is minus 0.02 to 0.02, 1/10. So the errors are less than 10% right there. Okay. Now look at the spread. What do you think about the spread? Is it constant? No. All right, so that's the key, that's the concern, that the spread is not constant, the errors do not have a constant standard deviation. All right. The only thing against that one could argue is that, well, they are less than 10%, so I don't care. All right. But that's an art. That's the thing that people can argue about. All right, I will leave it there. The straight line part is same thing. The straight line is almost there, except for this one point, which one could argue whether it is there or not there. A straight line, right? But this is much better than the other model. That is for sure. So, how do we interpret these results? So, these results basically say that the model is log y is a linear function of these things, and therefore y is 10 raised to q naught plus 10 raised to qa xa and so on and so forth. And if you put the values in of q naught, qa, qb, qab, then we get this model, that the mean performance is 1.07. When you have xa, which could be the processor, then the performance goes up and down by 0.107, factor of 0.107. Because if it is plus 1, this will multiply, minus 1, this will divide. Right? The workload also has the same effect. It goes up by 0.107 or goes down by 0.107, by a factor of 0.107. And the interactions, it turns out, has the same effect. This is just an example, okay? It turns out, I am really surprised that they have the same value. No, I think there is a mistake here. This is a typo. 10 raised to 97 is okay, but 10 raised to 03, this should be some small number. You have to write down, find out. The last number is digit is wrong. Oh, that 10 raised to 0.03 is written right here. 10 raised to 0.03 is 1.07. Oh yeah, okay. So this is 1.07 and this is 0.107. By the way, this is really interesting, is that 1.07 has no effect almost. Okay, you multiply by 1 or divide by 1, who cares? But 0.107 has significant, is big, because if you multiply by 0.107, it goes 1/10 by factor of 10, or it goes by factor of 10, right? So that is what was confusing me for a minute. Alright, so this is 1.07 and this is 0.107. Okay, with that, so how we say? We say that the time for an average processor on an average benchmark is 1.07. On processor A1 is 9 times that of an average processor. On processor A2 it is 1/9 of an average processor. So the factor is 81 times. The two processors are different by a factor of 81. Benchmark B executes 81 times more instructions than B2, and the interaction is negligible. Okay, so this is a multiplicative model, and basically in many of the problems that you are working on, you have to first think whether they are really additive or not before you really even try an additive model. So once we understand multiplicative model, then all of the things that we did for regression again apply, including the transformations. And so the transformations could be many. I think this transformation probably was discussed in regression. If not, we are going to discuss it here again. But we talked about how to find a function h given a function g, which tells you the spread. All of those things apply here. A common transformation method which is used in experimental design is called Box-Cox family of transformation, where you raise y to the power a and divide by some a z raised to a minus 1, and we don't know the value of a, so we estimate the value of a. And so this is all described in the book. I would let you read about it. rather than going through here. So there are other transformations other than just log. Alright, so now that we understand that 2 raised to k R design and what we can do in terms of transformation, we can just extend that to 2 raised to k R. And k R simply means that we write 2 raised to k terms plus the error terms. Parameter estimation is as before using the sine table. You get the same SSYs, SSTs, you get the same effects, standard deviation, contrast, predictions, everything else is same, the same assumptions, and then you have the same visual tests. And this is an example. I really don't have to go through this example, but basically these, instead of 4 rows, now we have 8 rows, 3 factors A, B, C, A, B, B, C, and so on and so forth. You divide that and you get the percentage variation explained. So here is the result. A explains 14%, B explains 5%, C explains 75%. Again, you can see that which are the most important parameters, and then you can calculate the confidence intervals to calculate which of them are significant. So let's see, did we do the significance? Here is the significance part. So you do the confidence interval, and this part is 0, everything else is non-zero. So the interactions are small and insignificant. Then the prediction the same way, you just have to repeat the same formulas for M experiments. And so now there is a case study. Now this is a case study for garbage collection. Everybody knows garbage collection? I think I asked you before too. Everybody knows garbage collection, right? Okay. This was probably an example I did it very first time when we were doing introduction to the course. So this is a case study. It has, so some people were designing some garbage collection algorithm, and so they had 4 factors: the workload, compiler, limbo list, and chunk size. Okay, probably limbo list is their invention. Okay, it doesn't matter what limbo list is or what it was, but limbo list is the thing that they want to try out, right? But that algorithm also has 2 parameters: chunk size. They could use 4k byte as the allocation and deallocation chunk for memory, or 16 kilobytes. Right, so those are really the 2 things, and these 2 things can affect the performance, so they put those there. 4 parameters, each of them at 2 levels. Right, so they have 2 raised to 4 design. And they repeated each thing by 3 times, and these are real numbers, so these are not made up numbers. They repeated each thing 3 times, so they have these 16 times 3, 48 numbers. This is the mean. They did the table, sine table method, and this is the final result: percentage variation and confidence interval. So now let us see. The A effects explain 34%. We should not even write this number here because this is not really, I is not, so that one, ignore that number. 34% is A, B is 52%, and AD is 12%. Everything else is not important and not significant either. Now, see, the insignificant parts are only this. This is only 2 insignificant. Both of them, All right. So now, given that, really we have to concentrate on 3 things: A, D, and AD. All right. Now let's see what is A, D, and AD. A is the workload. D is the chunk size. Now, what about the people who designed the limbo list? It doesn't have an effect. All right. So this is the thing is that they really wanted to see that the C has the most effect, but C didn't have most effect. it is the chunk size which has the most effect. So you could easily conclude that really if you wanted to improve your memory interaction, memory performance, all you do is allocate whatever chunk it is telling you, small or big. And doesn't matter what algorithm you use. Alright, so the conclusion is most of the variation is explained by A, D and AD. The variation due to experimental error is small, so that is one thing, is several effects explain less than 0.05% of the variation. Only AD is significant. Alright, that's it. That brings us to the end of this chapter.
Question.
Yeah.
So we've seen a few examples like that, we chose a small number of factors, we did very small number of experiments, 3 here, and we got lots of interesting results. Is that what typically people do? If I want to know if my algorithm is affected by A, B, or C?
Yeah, see, this is, so here I think, there is, so just hold on to this thought a little bit more because we are going to complicate things more a little bit. And, I don't have to. No, but at the simple level, at least you understand that now you don't have to put too much effort on C or B. If I was given more time, I will probably do 5 levels for D and A, and then do maybe 3 levels for B and C, just to be sure that I didn't miss anything. Right? I could do 10 levels for A and maybe 10 levels for D, because D is the most impacted one, and maybe 5 levels for A, and maybe 3 for B, so on and so forth. See what I mean? So first we find out what is the overall impact, and then we are not sure still, because we would have missed the middle someplace. Right? This is 2 levels. So then we say, okay, like this one has the most impact. Now we want to see whether it is going like parabolic, or it is just going at the end, or linear. So we do on D more, right? So we spend our time where it matters.
Yeah, but those kind of experiments will lead you not to mess with something, which may be important if it had more levels.
Oh, no. So the thing is, okay, so clearly again, let me repeat this thing. This experiment says that between the 2 ends of C, there is no difference. Whether C is -1 or +1, there is no difference. Alright? Now, C in the middle could make a difference. Right? So if you really want to be sure, you will run another experiment with the middle. Now, if it's quite possible that there is no effect in the middle, but there is something like this, and then there is something else. What can you do? Systems don't generally behave that way. Systems generally behave, more like one directional, unimodal, but they could be, 15 modal systems. Who knows? Yeah.
Replications allow us to get an estimate for the measurement error. Can we use it in the opposite direction and say, if we know what a measurement error to be, we can figure out how many replications we need to do for a thread?
Yeah, you can do that. So basically what we do is, particularly in simulations, we run a simulation, we think we are done, but it turns out that the errors is either too small or too large. Let's say errors are too large. Then we sit down and do the calculation and we say, okay, we need 10,000 more. We run it. So that, generally if it is too small, then we don't go back and do anything, but we verify that the errors are not too large. Alright, so let me finish this for today. Replications allow estimation of the measurement errors. That's the key part. Now with the errors, you can now do the confidence intervals, and for the predictions, for the parameters, for the contrast. And then we also learned the visual tests, and then we learned about the multiplicative models. Alright, so there is a homework 18B, which is, you just have to do 18. That's what I was missing. That in 18A, we did not do the other thing. So we are going to do percentage variation explained and conduct the visual test. So that will be complete homework.